Good and blessed day to all. I hope you are all okay. I am Mr. Arnel Equeto. Today, allow me to help you learn and understand the subject Discrete Math. So what about this Discrete Math? So this is one of the fundamental subjects in the discipline of computing. So when we say discipline of computing, there are 5 separate yet interrelated computing disciplines. We have computer science, computer engineering, information systems, information technology, and software engineering. If you are part of these disciplines, then you are also part of the computing discipline family. And you will needing to understand or study this discrete math. This is a very beautiful subject. So it is also a study of mathematical structures and objects that are fundamentally discrete rather than continuous. So when we say discrete, it is synonymous to separate, detach, distinct, and abstract. Also, the distinct is used as an adjective, which means individually separated or distinct. That is why discrete math is different from other discipline or form of mathematics. So examples of objects with discrete values are integers, graphs, or statements in logics. Now, concepts from discrete math or concepts from discrete mathematics are useful for describing objects and problems in computer algorithms and programming languages. Maybe you are now enlightened why the computing disciplines are studying discrete math. Simply because it is useful part of describing an object, like I'd mentioned earlier, in computer algorithms and programming languages. These have application in cryptography, automated theorem proving, and the most common for us all computing disciplines we have, or the software development. You are correct. That is the software development. So maybe you're wondering what's the use of this discrete math in cryptography. If you're familiar with cryptography, it is used most probably in security, securing our network, our programs, and the likes. You need a background in discrete mathematics on how you can encrypt data. Okay, so that is very useful, and most probably in software development, it is very useful, the discrete mathematics. Okay, so I hope discrete mathematics now is clear why computing disciplines needs to study this subject. Let's move forward. Now let us explore discrete math. So what about the subject contents of this discrete math? We have logic and proofs, sets, functions, integers and modular arithmetic, sequences and summations, countings, probability. We have also relations and graphs. So these are the most common subject content of discrete math, but again, it is not limited to these contents. Today, allow me or join me to explore one of the subject contents of discrete math, which is the logic and proofs. So what about logic? So when we say logic, this defines a formal language for representing knowledge and for making logical inferences. It helps us to understand how to construct a valid argument. And also logic defines syntax of statements, the meaning of statements, the rules of logical inference or manipulation. So I know you are most of you are familiar with syntax of the statements, because if you are working with your programming language or languages, you're encountering the error called, yes, you are correct, syntax error. So what about syntax error? This simply means that your code does not conform with the programming language format. That's why, for logic, programming language logic, that is why it give you a syntax error. Okay, so I know you are now relating the matters. Okay, that's good. Let's proceed. Now we have also propositional logic. Okay, a proposition is a statement that is either true or false. Let us have an example. The capital of the Philippines is Manila. What about this? Is it true or false? Definitely it is true. The capital of our beloved country is Manila. Another one, 8 times 8 is equal to 16 is another example of proposition or a statement. Proposition and statement are equivocal term. It's similar. Okay, so please don't get confused. So going back, is the proposition 8 times 8 is equal to 16 true or false? Definitely it's false, because 8 times 8 is not 16, rather it is 64. 16 is not the product of 8 times 8, but it is the sum of 8 plus 8. Another propositional or another proposition or statement, it is raining today. The value of this is, yeah, this is either true or false. Why? Because there are factors that we need to consider to really identify if it is true or false, depending on the location or the time when you say it is raining today. Okay, so let's move. We have also composite statements. So composite statement, more complex propositional statements can be built from elementary statement using logical connectives. So let's have an example of a composite statement. Let proposition A, it rains outside. Let proposition B be, we will see a movie. Combining these two propositions to come up with a composite statement, it will give us, if it rains outside, then we will see a movie. That's it. That is a logical connectives, or that's a composite statements. Combine. Now let's explore now the logical connectives mentioned. So what is this logical connective? So as I mentioned, more complex propositional statements can be built from elementary statement using logical connectives. And what are those logical connectives? There you go. Flashing on your screen are the 5 logical connectives. We have negation, which means not, and its symbol is tilde. Okay. We have conjunction. This means and. Its symbol is like a mountain, but it's not a mountain. The correct name of the symbol is a hat. We have disjunction, or its symbol is called bell, but it's like an inverted B, but again, it's bell. We have also conditional connectives, logical connectives. It is read as if statement, then statement, and its symbol is a single-headed arrow. And we have the last one, biconditional. It is its mean is that if and only if, then its symbol is a double-headed arrow. Please don't get confused with conditional and biconditional. Okay, so conditional is a single-headed arrow, while biconditional is a double-headed arrow. Okay, please familiarize yourself with this connective, logical connectives, and its symbol. Okay, Other symbol for this not other use the like inverted L. So that also a symbol for negation or not. Okay, have you familiarized yourself? Let's move on. The first logical connectives is negation. So what about negation? So let P be a proposition. The statement, it is not the case that P is another proposition. Called the negation of P. The negation of P is denoted by, again, what's the symbol? Tilde. A tilde, then the P which corresponds to a statement of proposition, and it is read as not P. So this simply means not P if we're going to read it. Okay. So let's have an example that the proposition P is equal to John is a programmer. If we negate it, not P is equal to, it is not true that John is a programmer. Or we can simply means that John is not a programmer. That is also correct. So that is negation. In negation also, we are going, or in this logical connectives, we are going to use truth table. So what about truth table? So a truth table displays the relationship between truth values, whether true or false, of different propositions. Meaning to say, in other words, or in my own words, I can say that a truth table is a systematic way or approach in which we can determine, create a relationship between truth values of a particular proposition or of different or combinations of different propositions with the use of logical connectives or joined by a logical connectives. So let's have the truth table values of negation. Actually, we have only two input or two statements here. We have either true or false. If it will be negate, if not true, obviously it's false. And if it's not false, then obviously it's true. So, but writing a truth table is throw all possible values of elementary propositions, and this value will be the output or possible values on the use of logical connectives. Okay. Again, familiarize yourself with the negation. That is negation. So again, that is just you are going to reverse in a other word. Reverse true or not true, false. Not false, true. Moving on. Let's go with the second logical connective, which is the conjunction. So let P and Q be a propositions. The proposition P and Q denoted by P. Again, what is the symbol, if you remember? This is, what symbol is this one? A hat. That is correct. A hat symbol. So it's true when both P and Q are true and false otherwise. The proposition P and Q is called the conjunction of P and Q. So this is a conjunction or simply and. P and Q. Let's go with the truth table of the conjunction. So we have 4 inputs here, or 2 propositions. We have proposition 1 denoted by P and proposition 2 denoted by Q. If this is combined together with a conjunction, true and true is true, true and false, false, false and true, false, false and false, false. Generally, we can say that P and Q is true only when both P and Q are true. Otherwise, if not both 2 propositions are true, it will give us a false answer. Okay? Again, familiarize yourself. There you go. Thank you. Let us now go with the third one, disjunction. Disjunction, let P and Q be proposition. The proposition of P or Q denoted by P, the symbol again. What is this symbol? The symbol is, okay, the OR symbol. This is, yes, a bell symbol. So this is read as OR. P or Q is true when there is one true to either P and Q and false otherwise. The proposition P or Q is called disjunction of P and Q. Okay, let's go with the systematic approach again through table. So you have two proposition P or Q. Again, if there is only one true, then the output will be true. Otherwise, if both false or all the propositions are false, that is then the time that we can get the false answer. So meaning to say, sir, it is the inverse or the reverse rather of conjunction. Yes, we can say that. That is correct. Disjunction is the opposite of conjunction. That's correct. You're learning. Okay, so very good. Let's continue. Conditional propositions. We are now at the fourth, logical connectives. A conditional or implication proposition is of form if P then Q. This is how we read the conditional or implication proposition. If P, then Q. Okay, let's have an example. Let the proposition P be John is a programmer. Proposition Q be Mary is a lawyer. Combining these two propositions with our conditional logical connective, we have if John is a programmer, then Mary is a lawyer. Okay. Systematically, by the use of truth table, we can have its value. So if true, if Q, if P, then Q. If true, then true is, then it implies as with T, true or T. If T, then F, it will be false. If false, then true, we have true. If false, then false, we have true. So what have you noticed? You're correct. We only have a false value if P is true. Okay, if P then Q is true when both P and Q are true, or true when P is false. Okay, that is if P is false, meaning to say if the true statement is true followed by a false statement, it will always be false. Okay, that's another trick or principle. If you observe, that's correct. Last, we have now the biconditional. So biconditional, let P and Q be the proposition. The biconditional, how is it read now? P if and only if Q is the proposition that is used when P and Q have same truth values and it's false otherwise. It is read again as P if and only if Q. P is necessary and sufficient for Q. So we have two ways on how to read this biconditional logical connectives. By the use of truth table, we can show that T, if and only if T will give us T for true. T, if and only if F, which will give us an F output. F, if and only F, T will give us a F output, and F, if and only F will give us a T or true value. That's very clear, you're right. In the biconditional, it will only give us true values if and only if the proposition have the same values. The propositions have the same values. That is. Now we have compound statement. So two or more statement with more than one connective. So that is compound statement. Let PQR be a simple statement, and we can form other compound statements such as this is compound statement already. We have P. How do you read this? Okay, P or Q parenthesis and R, P or parenthesis Q and R parenthesis, not P parenthesis or not Q, P or Q parenthesis and parenthesis not R, and many others. So that's the compound statement. So example of truth table for the compound statement P or Q and R. So we already have three propositions, and as you can see, if we have three proposition, we have 8 entries. Okay, and out of 8 entries, we have how many combinations do we have? Yes, it's 3 combinations. Okay, we have P, Q, R. So the formula actually of this one, you're correct. In creating truth table, we have 2 to the n, where n is the proposition, the number of proposition. In this case, 2 to the 3rd power, which will give us 8. This is 8. Okay. So this is the output of this one. Now let's explore how what is the best way to solve a compound statement. Okay, so tips for compound statement derivation. In using truth table, use divide and conquer technique. If you are familiar with divide and conquer algorithm, yeah, we can use it here. So wherein decompose the sentence to elementary and intermediate propositions. Meaning to say we are going to divide into smaller portion this statement so that we can fully understand or derive the output of the compound statement. You're correct. So follow the correct propositions, precedence like negation, simplify statement in the parentheses. So we can simplify those statements in the parentheses and those that have negation. So for easier derivation of a compound statement. So let's have an example. So construct a truth table for P. How do you read this? If P, then Q, parentheses, and not P, if, yes, and only if Q, parentheses. Simpler if we decompose the sentence to elementary and intermediate proposition as I mentioned earlier. Doing this, we have the negation of P. Let's decompose it. Then P, what is this one? Implies Q. P implies Q. Okay. And we have this one. Okay. So what about this one? Again, okay. We have if, how do you read this again? If P or not P, if and only if Q, that is. So we decompose this this compound statement into 3 proposition statement. Okay, we have this one, the not P, the P, if P, then Q, and we have the other one. We have P, if, and only if Q. So there you go. That's correct. So the conditional or implication, and we have the biconditional. So this one, condition. Now, let us now answer it. So it's now much easier to answer it because we already decompose or chunk it into a smaller proposition or statement. Yeah. So auxiliary compound proposition and their values, typically the target, unknown compound proposition and its values. Then we have this one, the output of not P will be this one. So not P, not true is false, not true is false, not false is true, not false is true. Then we have if P, then Q, we have true. If T, then P, we have true. Same with this one, true, true again, and true. So the first statement is true. Now, let us now combine all our decomposed sentence or proposition. And this gives us this final answer. Okay. So you can continue answering this in your seat. If you are following, that's good. Okay. So because this is only 4, we are needing another 4 here. Okay. So that is. So that is the simpler way. Again, simpler if we decompose the sentence to elementary and intermediate proposition. Do not, in a real life situation, do not attack the problem as a whole. If possible, divide the problems and let each smaller bits be solved. If it will combine together, it will be solved as a whole. Okay, that is the thought for the day. Thank you. That is the most common day-to-day application of this. Other than the application, most probably of this in our discipline. Okay. So let's have a mind treasure. Wow. There is a mind treasure. What is this? Can you treasure? Can you find the treasure? Okay. So can you please try creating the truth table for this compound statement? P or Q parenthesis, not Q parenthesis, sorry, again I repeat, P or Q parenthesis and parenthesis, not R, P and Q parenthesis, or we have bracket parenthesis, not R, parenthesis, not P, if and if P, and only if Q, parenthesis, and close bracket. Okay. So try figuring out the answer. Again, what's the technique? Correct. Divide, decompose the proposition. So that's the technique you are now learning, and I'm very happy that you are learning, and I hope you are enjoying what you are doing. Okay, so it is much faster to learn when you are enjoying. So I hope you enjoy this. So up next, in our next video conference, I'll be discussing logical equivalence, tautology, and De Morgan's law for logic. So that's all for now. And may the light of wisdom be with you all. Keep your faith and be safe. Thank you very much. Again, I'm Mr. Arnel A. Cueto. Thank you.